leading up to where we are with this session. So on Tuesday at the canola industry meeting, we heard a lot about canola as a low carbon fuel that had 90% of the greenhouse gas reduction emissions compared to fossil fuels. And we heard about how it was not only approved as a biodiesel for blending, but also as renewable diesel and also for aircraft petrol. We heard a lot about the clean fuel standards and new targets across different states as well as Canadian provinces, and how this was driving the expansion of the North American crush industry. We heard about how existing customers of canola and new protein customers are interested not only in the product, but the sustainability of our sector, and their interest in sustainable agronomic practices, such as the shift to straight cutting and the 4R stewardship. And we heard about the Canola Council's program supporting uptake of the 4R stewardship program to reduce emissions, and also their interest in increasing carbon sequestration. So then yesterday at the Canola Discovery Forum, we heard a lot about nitrogen fertilization management and how there's tools there that can help reduce emissions through more effective use of nitrogen fertilizer. The goal of reducing nitrogen emissions by 30% by 2030 was mentioned. And I did paraphrase one of Joy Agnew's comments, which I thought was quite good. That was, and what she more or less said was, as an industry, we can move towards this goal with positive benefits that are beyond greenhouse gas reduction, in that it can increase economic yields, and there's going to be all kinds of opportunities and programs to take advantage of that. So that brings us to today and the final session, where I'm hoping we can build on this ongoing discussion where we've talked about policy and management, and we can move towards talking about the plants and how, as a plant biology community, can think about how we can build on the positives of the crop that we work with, but also look to the future and see how we can move beyond just producing oil and protein and think about maybe producing carbon. So earlier on in the year, the Canola Week Planning Committee, we had the opportunity to have several brainstorming sessions about the program for the whole week. And something that was discussed a lot was having a session dedicated to greenhouse gas reductions and carbon sequestration. And this was for a few reasons. One, that there was the announcement a few years back, the 30% reduction by 2030. But then just over a year ago, there was also the release of the Guelph statement, where reducing greenhouse gas emissions and improving carbon sequestration was identified as a priority focus area for the agri-food system by our government. So even though we work with a crop that has a lot of positives, there is the looming reality that in Canada, agricultural soils account for 72% of nitrous oxide emissions, and we do work with a very nitrogen responsive crop. So to dig into this topic a little more, we put together a panel. We as the committee put together a panel of diverse experts from different areas. Two of the speakers you've heard from before in previous years, if you've been around the canola community for a while, and they're going to remind us of the current as well as the potential positives of canola. And then we invited two speakers who've worked in different cropping systems. One who is an expert in photosynthesis, specifically in response to climate change, and the other is an environmental scientist who's done a lot of work in corn cropping systems, which is another, as we all know, nitrogen responsive crop. So how we're going to run this, we have shorter presentations. We're going to run through each of them, and then we're going to open up for a little bit longer Q&A session. We'll bring the speakers up, both virtually and in person. So we're going to get going right away with Danielle Way, who is from the Australian National University. And Danielle, she's a Canadian and Australian in Australia, who worked at Western University for the past 10 years. And her research focuses on how climate change affects plant performance including the warming and rising CO2 and water stress in crops and forests. So with that, I will turn it over to Danielle, who's joining us from Australia very early in the morning. So thanks, Danielle.
Thank you. So can everybody hear me? We're good? I'll take that as a yes. Okay. So thank you very much for the invitation to be speaking here today. And good morning from Australia. So I'm going to be talking a little bit about photosynthesis, so how carbon gets into plants in the first place, and how climate change is expected to affect that. So I think you're probably all aware that CO2 concentrations in the atmosphere have been rising. And indeed, they've risen 50% since the Industrial Revolution due to greenhouse gas emissions and land use change. So this just shows atmospheric CO2 concentrations across time since we started measuring them in Hawaii in the late 1950s. And we recently reached over 420 parts per million CO2 for the first time in modern history. Now, those increases in CO2 concentration, as well as in other greenhouse gases, are leading to global warming. And globally, temperatures have actually already increased by about 1.2 degrees Celsius. As we look into the future, over the next 80 years or so, by the end of the century, the Intergovernmental Panel on Climate Change, the IPCC, they predict warming of around 4 degrees Celsius globally. But as you can see from this picture, which is a picture from the IPCC showing predicted warming under a business as usual scenario. So in other words, if we don't implement greenhouse gas reductions, for example, then places in the northern hemisphere, especially at high latitudes, so regions like Canada, are expected to see much greater warming than the average. And you can see that the Canadian prairies, you're looking at average warming of 5 to 7 degrees Celsius. So that's a really big effect on the crops that we're growing. Now, we also know that while we're dealing with climate change, we still need to be producing actually more food than we are right now. And so it's estimated that we're going to need about 60% more food within the next 30 years to feed a growing population of up to 9 billion people that have increasing demands for things like meat and a sort of Western lifestyle. And we also know that leaf carbon uptake, so photosynthesis, underpins growth and yield in plants. And so there's been a lot of interest in whether or not we can increase photosynthesis and use that to boost crop yields. And part of this sort of interest has generated some large-scale projects. The first one is realizing increased photosynthetic efficiency, otherwise known as RIPE. And the other one is generating C4 rice. And both of these are large-scale projects that are funded by the Bill and Melinda Gates Foundation. And we're talking about multi-million-dollar projects that have been extending for sort of 20 years. And the reason that under climate change, we might actually expect some increase in photosynthesis and some boost in yield, our understanding of that comes from these free air CO2 enrichment experiments. So these are known as FACE projects. And the upper two pictures here show you FACE experiments in crop systems and the bottom two in forests. So what you do is you build rings of pipes around a plot. So here you can see the crops growing in the middle. And then you blow high CO2 into those plots through the pipes. And so you can enhance CO2 concentrations on the plants that are growing there under very natural conditions. And what we learned from these types of experiments where you have natural soils and natural weather is that high CO2 increases photosynthesis in the field. And this is because CO2 is fixed from the atmosphere by the enzyme Ribisco. So Ribisco is just short for the full enzyme name, ribulose 1,5-bisphosphate carboxylase oxygenase. And that's in photosynthesis. So as you have more CO2 around the enzyme, you stimulate its uptake of CO2 in photosynthesis, and simultaneously you suppress a separate process known as photorespiration. And that's where the same enzyme Ribisco fixes oxygen instead of CO2. And that's generally considered a wasteful side reaction from the plant's perspective. It wastes carbon and it wastes energy that the plant has actually already taken up. So this is something that we're trying to reduce in crops and in other plant species. Now, if you go out to these FACE experiments and you look at this higher photosynthetic rate, what does that translate to for crops? Well, across a wide range of different crops, here you can see data for wheat, rice, legumes, root crops, and other sort of C3 crop species like canola. What you tend to get is on average about a 20% increase in yield. So that's what this sort of 0.2 means here. So fairly large increases in yield, and that's directly related to more CO2 coming into the plant, more carbon. Now, at the same time that high CO2 is going to boost photosynthesis, you're also having these warming effects that we talked about. And the problem with that is that photosynthesis is not just CO2 dependent, but it's temperature dependent as well. And so here I'm showing you how photosynthesis responds to changes in leaf temperature over short-term minute-to-minute sort of variation. And again, canola plants are going to be C3 plants, so they look something like this, where at low temperatures, photosynthesis is suppressed, and then you reach some sort of a thermal optimum. And you reach that increase up to a thermal optimum just because warming increases enzyme efficiency inside the leaf. But above that temperature, somewhere around 25 to 30 degrees Celsius, you start getting declines in photosynthesis. And so what that means is that the direct effect of temperature depends on where you start. So if we're operating below the thermal optimum of a plant down here, then a little bit of warming will actually increase photosynthesis. But if you're already up in a plant that's heat stressed and is above those sort of temperatures, which is what we're going to move to under climate change, then instead what you're going to get are suppressions of carbon uptake and therefore suppressions of growth and yield. So layered on top of those sort of very simple responses of plants, or at least photosynthesis to CO2 and temperature, is the fact that, of course, plants don't just, but they're not static, right? And so they acclimate and adjust to their environment over time. And I'm sure you all know that. So under long-term exposure to high CO2, so for example, when you grow a plant at high CO2, that initial stimulation of photosynthesis tends to gradually be suppressed and wear off. So if we take a plant and we move it from 1 minute to the next to high CO2, you might see a boost of, say, 40% in photosynthetic rate. But if you leave it there in something like a face experiment, gradually over time, that reduction, that boost in photosynthesis is reduced. And instead, you're at more like that 20% increase in photosynthesis. Similarly, plants acclimate to temperature. And so if you have a plant that's been exposed to a cool temperature, then if you have the photosynthetic rate up here and leaf temperature at the bottom, then that cool plant will have a photosynthetic rate something like this, where it's optimized to have high photosynthesis at low temperatures. And if you take that plant and shift it to a higher temperature, instead what you see is a shift in that thermal performance curve. So you tend to see enhanced performance at higher temperatures. And this is the sort of thing that we would expect would help offset negative responses to warming, is that the plants will adjust and actually do better than they do currently under those warm temperatures. The problem is, although this is what we expect in the majority of species, and we see this in about 50% of the species that we study, we also see a lot of circumstances where plants cannot acclimate to that increase in temperature, even if it's not huge. And so this is data from my own lab showing photosynthetic rate here. Sorry, it's A, assimilation, so CO2 uptake in plants across a range of different leaf temperatures. And these are for Canadian tree species. And the blue represents plants that have been grown at cool temperatures, so the temperatures that they currently grow at. The purple are plants that have been grown for their entire life cycle at a 4-degree warming. And the red are plants grown at 8 degrees warming. And so the idea here is what you're seeing is this gradual suppression of the ability of the plants to uptake CO2, which is going to affect growth, it's going to affect yield, and it's going to affect our ability to sequester carbon in these systems. So where we're moving to is this idea of trying to identify climate resilient plants so that we can actually be planting the varieties and getting traits into breeding programs that will increase photosynthesis, increase growth, and increase yield in crop species. So to do that, we need to actually characterize plants grown under the future CO2 and temperature conditions we're expecting for the next 30 to 80 years. And for crops, that means not just looking at yield, but also nutritional quality. And this is often something that's not studied. But if you grow plants at high CO2, when you look at grain crops especially, then what you tend to see is a suppression of the protein in yellow, as well as micronutrient contents such as iron and zinc in the seed. And so this is data for wheat, rice, and maize from a suite of these sort of face experiments showing, up to 9% decreases, for example, in zinc concentration, and about 6% decreases in protein in the seeds. So currently, one of the projects that we're working on is looking at whether or not there's variation in the climate resilience of Canadian wheat lines. And so we have 20 wheat lines in the study, 14 of them are Canadian spring wheat, and these are being grown under different climate scenarios. So we have current CO2 as well as high CO2, and that's the CO2 concentration we expect around the year 2050, so 30 years from now. And then warming of nothing, so the control temperatures that we currently have in Saskatoon. And then a +2 and a +4 degree warming, again, looking at the sort of warming we expect in the next 30 to 50 years in the prairies. Now, this is work being done by my student, Andrew Cook, in collaboration with Raju Sulanayakanahali, who gave a talk in the earlier session here at Canola Week. So to give you an idea, we've just harvested these plants a few weeks ago. And this is some preliminary data just showing plant height for these 14 different wheat varieties. And under current CO2, so ambient CO2 over here, current temperatures, 0 degrees warming, just current temperatures, there's quite a bit of variability in these different lines in the height, the growth that they achieve. And we've highlighted the best performing variety under each condition here in a black box. However, under current CO2, what you get is this large suppression of growth in the plants as you increase warming. Even just a 2 degree warming, which is the sort of thing that we'd expect easily in the next 30 years, shows big drops in the growth of the plants. Now, under high CO2, as we go from current temperatures to that small degree of warming of 2 degrees, we tend to see rather a stability in the ability of the plants to grow. And this comes back to those effects of photosynthesis. Under high CO2, that suppression of photorespiration, so that wasteful side reaction, means that the plants have more carbon available to dedicate to growth and to yield. However, what you can see is that under the 4 degree warming, even under high CO2, we get these suppressions of growth. And really what we're looking for are these plants that perform particularly well under these high CO2 and warming conditions, as opposed to these sorts of lines here where you get strong suppressions in growth with warming. And I'd like to highlight that you get some surprises. So the worst performing line under current conditions here was actually the second best performing line under high CO2 and warming. It's this orange dot sort of hidden behind the green one. So it's not just growth, but also traits that are related to yield. So we're still actually threshing and getting out the seed itself. But this is data on the total grain and ear dry weight of those different varieties. And again, you can see under current CO2, warming really suppresses these reproductive traits that will result in reductions in yield. But there's quite a lot of variability that we could start playing with in breeding programs. And similarly, under high CO2, a little bit of warming might actually enhance growth of these plants in the next 20 to 30 years. But then over the next 50 or 60 years, we would expect to see we've pitched over a threshold and we're going to have suppressions of growth and suppressions of yield. So I realized, I've just moved to Australia. I'm Canadian. I'm escaping the Canadian winter that you guys are undergoing right now. But this is what we'd like to think that climate warming will look like in Canada. This is a picture of a beach in Lake Erie where they actually bring in cranes and plant palm trees in the sand to make everybody think we're tropical. You can see the Canadian flags. But as a high latitude country with a lot of natural resources in both forests and crop species and agriculture, we're really at high risk of climate change. And so I just want to highlight that higher photosynthesis does increase yields. And if we can increase photosynthetic rates in crop species, then we should be able to realize enhanced yields. However, climate change may not lead to higher photosynthesis. Elevated CO2 does, but warming may negate those CO2 effects. And so there's really a strong need to evaluate crops under the climate conditions of the future to evaluate which traits and which genes actually enhance performance under future climate change, so that we can enhance carbon assimilation into the plants for yield, but also for carbon sequestration, since that's where that carbon is coming from in the first place. So thank you very much for your time. And I'll be happy to take questions during the panel discussion.
Thank you, Danielle. So next we're going to invite Claudia Wagner-Riddle to give another virtual presentation. Looks like we see Danielle, so hopefully we see Claudia in a minute. But Claudia is a professor at the School of Environmental Science at the University of Guelph. She's an expert in the measurements of greenhouse gas emissions to determine the carbon footprint for food, feed, and fuel produced by agriculture. So welcome, Claudia.
Can you hear me okay and see me?
Yes, we can hear you and see you. Thanks, Claudia. Go ahead.
And see my slides. Great. Thank you. So thank you for the introduction. And so Danielle's presentation talked about more the adaptation to climate change. My emphasis will be on the mitigation of greenhouse gas emissions, in particular, the role of nitrogen in greenhouse gas emissions in agriculture. So I'm going to start off with with a few kind of headlines. You may look at this and say, well, where's the canola? But I will make the link to the dairy farmers target. In addition, a lot of big food companies have pledged for net zero emissions. And in the introduction by Sally, we heard about biofuels and the interest in the carbon footprint of biofuels. The idea is like a lot of these larger food companies, they can look at on-farm emission reductions contribution towards their net zero goal under what's called scope 3 emissions. So those emissions that are upstream from their business, but that they indirectly affect. And the important thing here is that often more than 90% of food companies' footprint is due to on-farm emissions. So what do we mean by net zero? It's really balancing those greenhouse gas emissions with the CO2 removal. So I think there's been a large emphasis in the last number of years on carbon removals, particularly in Western Canada, because with the adoption of no-till, there was an increase in carbon sequestration, but we're seeing that amount leveling off, and the emissions will continue increasing because they're related to nitrogen. So in my talk, I will focus on the reduction part of the greenhouse gas emissions. And for that, first, I want to just giving you an overview of the gases of interest overall in agriculture. The top one is methane, but a close second is nitrous oxide. And nitrous oxide is the main gas of emissions from cropping systems. Now I have here 30%, and you heard Sally mentioning 70 or so percent. That is if we look at the budget of only nitrous oxide, while here we're looking at overall all the greenhouse gases. So the focus here, and particularly for a crop like canola or corn, that's where the large emissions are occurring. Now, these cropping N2O emissions are all related to nitrogen losses from soils. I like to use this diagram that I borrowed from Craig Drury at Agriculture and Agri-Food Canada that depicts the nitrogen cycle in a little bit of a simplified way. But if we add forms of nitrogen as the most commonly used shown here, we can think of it as this nitrogen going through a pipe that has several valves through which losses occur in various forms of nitrogen. Of course, we want that nitrogen to end up in our plant here. As introduced, I will focus on corn because that's the work we've done. And when the loss occurs in the form of N2O, that's what we term the direct N2O emissions, but it can also occur as ammonia or into air or nitrate into water. And those losses eventually will end up somewhere where they can also result in N2O emissions, and that's our indirect component. So ammonia losses, controlling those are obviously keeping more of the fertilizer to where it should be going into the plant, but it's also contributing to reduction in fertilizer-related emissions. So as I move through my presentation, I'll be referring back to this diagram as a good way to sort of think about how can we decrease these losses so more of the nutrient ends up in the plant. So back to the milk production, Dairy Farmers of Canada will be looking at meeting that set goal of net zero by 2050. And of course, there's a lot to do related to enteric fermentation or manure management, but 30% of the carbon footprint of milk production in Ontario, and it shouldn't be that different in other parts of Canada, is due to the feed. So thinking of things like corn or canola that are ingredients to feed, there's an interest to also reduce this part of the pie in terms of the whole carbon footprint of milk production. If we look to specifically corn in Ontario, this is work that an analysis that we did a while ago, but where we were comparing improvements over time. And there have been similar analyses done for canola. We do see quite a bit of improvement in the carbon footprint, which is expressed as CO2 equivalent, so that we can add all the greenhouse gases into sort of an equivalent currency expressed per ton of grain. And in this case, we see that 70% is due to nitrogen management, including the upstream or emissions to produce the fertilizer. And then about a third is the fertilizer related emissions that we've heard a lot about lately. So we really need to look at how to develop and assess mitigation practices. And this diagram kind of shows the different steps that we need. So obviously we need to measure at, and there are different types of measurements. In my group, we do quite detailed year-round measurements shown here in these towers, but also manual sampling using chambers. We then get close to year-round data. We use this to inform models that we can run at a larger scale, and then couple that with economic analysis and developing a roadmap for net zero emissions. I won't have time to go through all of these components, so I'll focus on sort of a few example mitigation practices, the measurement and this kind of summary of that. But before that, to devise any kind of mitigation practice, it's important to understand when the N2O emissions occur, because then we can actually look at specific regions and soil types to determine what would be our best option to try to mitigate. And a term that I've used in my presentations to think about this is that they occur in hotspots and hot moments. So hotspots at a more micro scale can be the injection slot of fertilizer, in the case here, side dress to corn, or in a field. And I dropped in a few sessions yesterday that I heard a lot about precision management. So that would apply at this scale. My group has also done a lot of work with freeze thaw, which I'm not going to go through today, but the thawed areas are also times when we have high emissions. So concentrating on the fertilizer aspect, if we apply nitrogen at planting and then, wait for rain, which is what everyone does as a farmer, then we get these big peaks of emissions. If we don't have the fertilizer application, we don't get them, or we get them, they're much smaller. Now, of course, we need fertilizer to grow crops. So our task is to how can we manage this in a way that those hot moments where we have reduced emissions. So these tend to occur in wet conditions, high N levels, and low crop N uptake. So it's really about going back to this diagram, optimizing that N use through practices that reduce these leaks. So thinking about what are some ways that we can reduce the ammonia loss, reduce the nitrous oxide loss, and reduce the nitrate loss, and in fact, make the system more efficient so that more of the fertilizer ends up in the plant. And the 4R nutrient stewardship program is a good framework for this. Now, of course, the big question is what is right? And that, I think we still have a lot of work to do in terms of research to determine what the right practices are for reduction of emissions. So I'm going to give you just a couple of examples. And I like to think about it like we're really trying to manage those hot spot and hot moments with the 4 R's. So using the right source is, well, it can be several things, but one in particular is the addition of inhibitors. So if we inhibit this process, both the hydrolysis of urea and nitrification, we slow down the process so that we get less nitrate at any given time and reduce those losses. The research that we've done has been with these 2 compounds for both a dual inhibitor and reduction we've seen in 2 out of 3 years and 40% on average, so quite a significant reduction. The next practice, I find this really neat. I, again, borrowed this from Craig Drury because it really demonstrates this, like how we're managing the hotspots. So in this case, instead of injecting in one slot, he injected in 2 slots at half the rate. So overall, it's still the same rate, but less concentrated. And saw really large reductions. Oh, actually, this is wrong. This should be 53% instead of 16, which just the double slot. But if you then also add a dual inhibitor, the reduction is 53%. And a really large reduction in ammonia losses, which then also increased yields. So one way to think about this is, can we manage the leaks better with right source, right place, and right time, which I didn't talk about, so that we don't have to turn on the tap as much. So here's where savings could come in for producers. And it's really about stacking practices. In modeling, we've shown that using injection, adjusting the rate, and as adding dual inhibitor, we could have a reduction of 60% on average, and this is over 30 years in N2O emissions. So my last slide here is that, just summarizing, there's great interest in agricultural climate solutions, such as the ones I talked about. There are a number of promising mitigation practices, but I do think that there is more innovation needed to improve crop nitrogen use, particularly better products. The inhibitors that we are using are many years old, and also looking at the whole cropping system, like rotations and so on. And in my view, Canada can be a leader in innovation for these types of technologies, because that is something that a lot of industries are after in terms to implement net zero emission plans. And with that, thank you very much for your attention, and I'm looking forward to questions.
So next we're going to invite to the stage Brian McConkey. Dr. Brian McConkey is a chief scientist at Viresco Solutions, which is an environmental consulting firm. And he works by helping clients in the agriculture value chain strategically navigate the complex and evolving world of sustainability. So prior to joining Viresco Solutions, Brian had worked for 33 years at the Swift Current Research Station with Agriculture and Agri-Food Canada. We believe it was 2017 when he last spoke to us, so we're excited to hear what he has to say today. Thanks.
Yes, well, thanks for inviting me, and it's great to be here in person. Yeah, I think it was 2017 I gave this talk on cool canolas, and then they asked, can you give an update? And there has been some really important new information that's come in, so this will be quite a a much more hopefully accurate sort of presentation. We were kind of hypothesizing before. Now I think it's starting to see that come about. It doesn't work. It's not moving. Oh, there. Okay, sorry. Yeah, so there was a paper in 2017 that said, well, what do we need to have, in terms of real system changes to get a lot of carbon sequestration to create what's called climate smart soils. And one of the biggest ones was we wanted a crop with more roots and other residue carbon, because that would, of course, increase the carbon input and through that increase the soil organic carbon and achieve carbon sequestration or carbon sink. And it turned out we had that crop all along, and that crop was canola. And when we look at it, we can see that that even growing under the same sort of situations, that comparing it with spring wheat, that there's much higher, particularly below ground residue production. Canola produces more more roots, but also due to its low harvest index, it actually then also produces more straw carbon. And I just provided a couple of pictures with that type of sort of residue production, and often you kind of underestimate the amount of residue that canola is leaving on the ground when you look at it versus cereal like wheat, but it does actually produce significantly more residue, at least by all the measurements for Canada. And so looking here, this then I went through, and so Canada has now started reporting the effect of carbon input on crop residue production and soil organic carbon, and so they have this model of soil organic carbon that's in response to carbon input, and so like IPCC Tier 2 doesn't really matter, but that's what they're using, and it's a pretty well accepted methodology. So I just looked at the mean for 2017 to 2021 using that methodology and got the average carbon input for the different for the crops. So this one would be an area weighted average for all the other crops that are grown on the prairies, and this one just for canola. But you can see that it is about, like in Saskatchewan, pretty much that 1.5 times, and but not maybe quite as high in Alberta and Manitoba, but it is significantly higher than any other crop. And also the other thing that's been going on, of course, is that crop yields themselves have been increasing, and we can see that corn has more prairie corn has more than doubled, canola has more than doubled in sort of a 4 decades or so, whereas something like spring wheat hasn't increased as much. And but this also, of course, is contributing over time to the increase in the amount of carbon. And so this then leads in so I'm pulling this from Canada's last 2022 National Inventory Report. So that's where Canada reports its carbon. As I said, this is the first year it started including the effect of crop residues. And so all these big orange lines here, that's really just from the crop residues, and we can see that that it's kind of overwhelming a lot of the other changes. Like there's a smaller here is the changes in tillage system, which is much smaller. So, and then if you compare the 2021 report, which didn't include the impact of crop residue inputs, versus the 2022 for the same year, 2019, you can see that it's more than doubled the amount of the sink that was occurring. That's across Canada, but not most of that's in the prairies. So this really makes quite an impact then on the amount of carbon that's going, amount of soil carbon increases that are happening by including the carbon input. So as a result, then canola is good for soil organic carbon, and so I did some of the runs with this carbon input method, and if we just started growing canola, like new canola, and compared that to growing other crops, like again that kind of weighted average of other crops on the prairies, you'd get like a 650 kilogram of carbon per hectare per year boost kind of initially, but even after 20 years, you're still getting a boost of about 130 kilograms per hectare of carbon per year. And there are some long-term increases that would kind of be, that you can see experimentally that would support that sort of at least long-term sort of rates. So this effect is fairly important. And so, and why is that important? Well, obviously that large soil organic carbon increase, that creates a carbon sink that helps Canadian agriculture reduce its net greenhouse gas emissions. But the rules for accounting for that soil organic carbon increase in the carbon footprint are not finalized, but somewhere there has to be some sort of recognition for it. But some recent carbon footprint analysis was done for the Canadian Roundtable on Sustainable Crops. And so the one that was done previously, sort of not considering carp residue input, the carbon footprint for canola was 383 kilograms of CO2 equivalent per ton of canola seed. And then it just redid one for 2019, but now including the latest soil carbon increases, and it decreased that carbon footprint down to 139 kilograms of CO2e per ton of canola seed. So that's a huge reduction. That's really just from doing a better inclusion of the amount of soil organic carbon increase in the prairie cropping systems, but also point out that as I said, there's sort of extra carbon that's coming just from growing canola versus growing some other crop. And in fact, that's not included in that number. So probably the actual, I mean, if we do need to do some work to decide sort of a fair way to sort of include this. The problem with all this is with carbon change, you're always comparing something with something that doesn't, something with a sort of a counterfactual other, but so there's always a bit of difficulty. But if we could, that was included, of course, it would even lower the carbon footprint more. So this becomes particularly important in biofuels, and so the feedstock generally dominates the carbon footprint of the biofuel. So and the value of carbon can be quite high. So the British Columbia low carbon fuel standard, the October 2022 value for a credit, which is like 1 ton of CO2e, averaged like $447 and change per ton of CO2 equivalent, and was as high as 519 during 2021. So there's a huge value for the CO2 reductions by having a feedstock with a low carbon fuel that sort of overwhelmed the regular price of carbon. And that's just because of the strong demand for low carbon fuels because of these carbon standards. So now that we have the National Clean Fuel Regulation, that's going to operate similar, because it's based again on a similar carbon intensity basis, very similar to the BC low carbon fuel standard. So that'll increase the demand for biofuels from feedstocks with a low carbon footprint. So there's a real potential here and a real increased market for canola, because it is particularly beneficial. And of course, the prairies are also beneficial, give it a particular benefit because of the nature of our soils. And in some ways, we're getting a lot of carbon increases now because they were degraded over many, many decades with a lot of summer fallow. And so we're picking up some of that, but it's, we need to, these are advantages that we have and that we can take advantage of. But of course, it's more than just the soil carbon. And of course, a big thing that affects the heat is just how much of the solar radiation is reflected back out into space. And so the land surface reflectance has a very important cooling effect. And in fact, like planting a coniferous tree in a snowy place usually causes more warming than it would ever cause from the CO2 removal from the growth of that tree. That's just a coniferous tree. And also, we knew from some work that canola is a very reflective prairie crop, especially when it's flowering. I think anyone that's driving through canola fields, you pretty well need to make sure you have your sunglasses on when the canola is in flower. It's obviously very reflective, but it makes it, that adds a lot of cooling. But now we have a better idea because of some work done by Jinghui Liu and al. At in AFC Ottawa, looked at this effect for it was actually specifically for Saskatchewan, and they kind of extended it to the prairies. But the this reduction in radiative forcing through this increased albedo or reflectance has a large effect. And when they calculated it, they looked at just, what's happened. We've seen an increase in canola area since 1990, 2019. What was the impact of that on warming? And it was like 57 million tons of CO2 equivalent. Like, that's huge. That'd be way more than that extra soil organic carbon coming from the canola plant itself. It's really that reflectance is actually hugely important. Of course, we don't really think about the reflectance, and I didn't see anyone talking about it as kind of a breeding objective, but obviously this can have a huge impact. But we've also, the other thing too is that canola, of course, is very, as we know, well suited to no-till production. And they looked at just the impact of no-till. Of course, it also has a huge advantage by increasing the reflection. And in fact, so that, if we consider canola as part of the, as a contributing factor that allowed no-till to expand, and that was equivalent to 180 million tons of CO2e. And so that was, that was more than about double what the impact of reduced tillage on CO2e simply from the carbon sequestration. So we keep thinking, well, reduced tillage was important for global warming because of its impact on soil carbon, but actually it had a much bigger impact on cooling simply because it increased the reflectance. And so over the whole year, though, I guess we discovered it, or they discovered, Xingui and Liu, that it was certainly much more reflective than spring wheat for whatever reason. But there's other crops that have pretty similar reflectance in barley, lentil, and pea, where some that were all sort of in the same ballpark as canola. So it isn't necessarily, there's not, I don't think any crop that's more reflective, but there are other crops that seem to be as reflective. So this, generally this radiative forcing from albedo changes isn't really included with sort of the greenhouse gas effect, but they're really important for land management. I guess that's why they're kind of unique to where you're changing the surface of the land, and that's really something that agriculture does all the time, every year, and so it's kind of maybe more peculiar to agriculture, but as it shows here, actually can be very important. So then to summarize, then canola produces more carbon input from above ground residues, and particularly root residues, than other common crops, and this increases the prairie soil carbon sink. But canola also cools the planet by reflecting more sunlight than many other crops, such as wheat. And I guess I got a mistake there. But therefore, canola provides more climate change mitigation because of its carbon sequestration benefits and its positive albedo. So these two things should be considered together. So these lower its carbon footprint. We talk about a carbon footprint as if it really means something in terms of carbon. It actually has nothing to do with carbon, and it's entirely about radiative forcing. So this is why the albedo is, because it's a part of radiative forcing, should be part of what's usually called a carbon footprint. And so it also should be, so it should be sort of the preferred oilseed for food purposes for companies with emission targets. It has all these real positives, and many companies have these pledges. So why not source Canadian canola to do it? But also, the biofuel market may be, a really attractive place to be selling canola as a preferred feedstock for biodiesel or biojet fuel. But there's still work that needs to be done to have these climate mitigation benefits recognized to extract the full value of canola. So, including the so-called carbon sequestration benefits and particularly positive albedo effects in the carbon footprint, there's still a lot of work, and I've been doing some work with that actually with the Canola Council of Canada, but there's still a lot more yet before we can sort of fully use them to extract the full value of canola in terms of its impact on sustainability. So thank you.
Thank you, Brian. So our final presentation is going to be a recorded presentation from Wolfgang Busch at the Salk Institute. So Dr. Busch is a professor and holder of the Hess Chair in Plant Sciences at the Salk Institute for Biological Studies in La Jolla, California. And Dr. Busch, he studies genes, genetic networks, and molecular processes that determine root growth and its responses to the environment. He's also executive director of the Salk Harnessing Plants Initiative, which I'm hoping he'll tell us a little more about. So I'll turn it over to Dr. Busch.
This slide from the IPCC 6th assessment report, where the International Panel for Climate Change really this slide from the IPCC 6th assessment report, where the International Panel for Climate Change really maps out where we stand with our emissions and with models how we can limit global warming to a certain extent. And as you can see here on the left of the slide, there are 3 scenarios outlined. On the y-axis you see the annual greenhouse gas emissions in gigaton CO2 equivalent per year that is modeled in these emissions. And then there are 3 temperature scenarios that range from 1.5 degrees Celsius average temperature increase globally until the end of the century to 3.2 degrees Celsius average temperature increase globally by the end of the century. And you can see if we continue to burn and to emit fossil fuels and CO2, to burn fossil fuels and emit CO2 at the current levels, it's depicted in this red scenario, we will end up with an increase of 3.2 degrees Celsius by the end of the century, which actually will have very dramatic negative consequences on many aspects of the human global civilization, including our ability to produce food, feed, and fiber, but even probably entire parts, in the equatorial region will be deserted because it will be too hot to live there. So really, the hope is that we can limit global warming to 1.5 degrees Celsius or 2 degrees Celsius, which will come with tremendous consequences, but they are still manageable according to many scientists who study these scenarios. But what we need to do there, and you can see that, is that we need to reduce emissions dramatically. So even for the 2 degrees Celsius warming scenario, we need to more than halve our global CO2 or greenhouse gas emissions, which is a tremendous endeavor because we are pretty much dependent on many fossil fuel dependent processes, and so even if we will continue with the rate of adoption of regenerative energy, solar and EVs, it's hard to imagine at the current pace or even at increased pace to get there. So all these more moderate scenarios need actually a drawdown of carbon dioxide from the atmosphere. So thinking about plants in this scenario, clearly the global temperatures will increase by a substantial amount until mid and end of the century. And so we need to think about how can we adapt crops to a different climate. For some crops it's easier than others. Some crops you can migrate, but some crops, for some crops it will be really too hot to produce seeds, for instance, in some areas. Another thing we should all think about, how can we actually reduce agricultural emissions? Agricultural emissions are a huge contributor to global warming, and a large part of this actually relates to nitrous oxide emissions that come from fertilizer being converted by soil microbes into nitrous oxides, which is many times more potent as a greenhouse gas than carbon dioxide. So thinking about smart agriculture that reduces nitrogen input and also loss of nitrogen through these microbes will be very important. And the third one, I'm going to talk about this, is plant-based carbon sequestration, which will address, hopefully, how do we actually draw down carbon dioxide at the scales that are necessary to reduce our net emissions as substantially as needed to achieve a 2 degrees Celsius or 1.5 degree scenario. And we think there is a lot of hope in that, because plants are the most sophisticated machines, so to speak, to catch carbon dioxide and fix it into biomaterials. So the question there is, how can we actually stop some of these fixed biomaterials, some of the plant material, to rot away, to decompose as quickly as it does right away? And that's what we are thinking about at the Salk Institute, where we kind of like came up with a concept that we call the Salk ideal plant, thinking about 3 simple traits that we might enhance to increase the ability of plants to put more carbon for longer in soils. And these 3 characteristics are deeper root systems. The deeper the carbon that root systems are made of and that they are producing through and putting into the soil, the deeper that is in the soil, the longer it will stay there, because there's less microbial activity, less oxygen in deeper layers. So if we put the root carbon deep, we're gonna actually store it for a much longer time than now. The other thing is, of course, put more carbon in the root. If you put that deeper, that will be a great double effect in just having more carbon that stays for longer in the soil. And the third aspect is to think about the biochemistry of root systems. There are not all components that molecular components that roots make are degraded at the same rate. This is of course dependent on the soil type and the soil chemistry and on the temperature and others. But generally, there have been in the literature several studies that actually have linked things that are like highly reduced, like suberin, to have a longer lifetime in soil, so they stay longer around. And we are focusing on a molecule called suberin, which is the constituent of cork that all plants make in their root system. We want to make more of it so that it stays for longer in the soil. Do we think that that might actually be a feasible way to store and lock away carbon through carbon sequestration? We think there is. There are 2 main large ideas that relate to this. One is there is a tremendous capacity of soils to store carbon in addition to the carbon that's in them. We know that because we can look the other way around. There have been studies that have looked at the loss of carbon in agriculturally used soils. So when prairie got converted or other types of natural ecosystems in soils, that usually was accompanied with a loss in carbon. And in the study, for instance, from 2017, Sandeman and colleagues quantified this in a modeling approach and came to the conclusion that 133 gigatons of carbon has been lost in agricultural soils. And so when you think about it, that's the capacity to backfill some of this. It's an enormous carbon sink. So we don't think in many regions we will reach the saturation level soon. So there's enormous potential to store carbon in them. Another notable thing we thought about very early on was, if we want to change plants to store more carbon for longer by changing their root traits through breeding or gene technology, what types of plants do we want to focus on? And immediately it became clear, because each optimization requires a lot of work, we should focus on a handful of agriculturally used and prevalent species, because there's so much acreage on this planet covered by these species. So by focusing on a handful of species, you can make already a lot of progress in terms of the total carbon storage capacity. And we picked wheat, corn, rice, soybean, sorghum, and canola because they are some of the most prevalent crop species. And if you think we could replace the current varieties with with varieties that are better in storing more carbon for longer, that can have a huge impact, a gigaton impact, in fact, per year. We're basically using a two-pronged approach where we try to identify genes and genetic mechanisms that we can leverage to make plants better. We identify carbon sequestration trait genes in model species, develop a lot of technology, but do the same actually in diversity panels of crop species. And then we can actually using genome engineering to test whether these genetic variations actually work. We evaluate this in the greenhouse and test and validate the plant traits and the carbon accumulation in the field. And so you can use that, of course, also once you know which alleles and variants in a certain crop population are associated with enhanced carbon sequestration. You can use genomic selection as well. Just one example, we could identify genes in Arabidopsis, for instance, on the left, where if you change just one gene, in fact just one base pair in the whole genome, we could switch this rather shallow root system depicted and traced here in red to a deep root system traced in red on the right side. The difference of these two plants is one base pair, a stop codon in a certain gene. That's a deep rooting switch. On the right you see soybean plants that basically where we actually have advanced imaging to capture the 3D structure of the early root system, and we were able to look at different root traits and that will confer different root depth in soybean over several hundred accessions. And so we identified, and that's just the data here, two soybean varieties that have tremendous differences in root mass and also in root depth, where we on the right there's a deep soybean strain, on the left there's a shallow root soybean. And we went in the field and asked whether the root mass in the greenhouse is actually correlated to the root mass per depth, and we actually found a strong positive correlation in the field. That was from one season, so I will show you another, hopefully next year I can show you, data from 2 seasons and more genotypes. So far we actually have found that the traits that are associated with better carbon sequestration hold up from the greenhouse to the field. We are just now starting, or we just have now started doing the same with canola in a panel of winter canola. We actually also identified tremendous differences in these root system traits that relate to deeper rooting and a different root biomass. And those are 4 examples here, where on the left we have very biomass-rich root systems, and on the right we have more sparse root systems. And these, some of these lines are growing actually in Kansas right now, so they were sown at the end of September, and so hopefully we can replicate what we have seen in soy and can then progress in our research program to really identify the genes and the alleles that drive these differences in root traits, and then get optimized root systems for carbon sequestration. So we do a lot of things. We really have set us very audacious goals. So we want to have 1 megaton of carbon sequestered in 2027. So we are thinking about rolling out varieties with partners that could actually do this. And then in the 2030s, hopefully we will have gene-edited varieties of multiple crop species, or specific breeding programs in these to have a multi-gigaton impact. And we're working with partners, and we in fact funded a company very recently to actually achieve this and bring our technologies out into the world. With this, I want to thank you and acknowledge everyone involved in here. All the plant faculty members at the Salk Institute are working together in this Harnessing Plants initiative to make this a reality, and we were able to generate very generous funding from a number of sources. And with this, I thank you for your attention.
Thank you, Wolfgang. So with that, I'd like to invite Brian back up to the stage, and we do have Danielle and Claudia and Wolfgang all online to answer some questions and hopefully have some good discussion. I realized I forgot to introduce myself, so I'll do that now. My name is Sally Vail, and I'm a canola breeder with Agriculture and Agri-Food Canada here at the Saskatoon Research and Development Centre. And my co-chair, who is moderating the online questions, is Larry Cernick down there, so you'll hear from him in a bit. I'm really excited about the question. Larry said there's lots of questions online, so I'm excited and hoping there's some people that are willing to step up to the microphone as well. Given the nature of this panel with such diverse speakers, I'm really excited about the questions that more than one speaker can and will answer, we hope. So with that, I will open up to the floor, see if there's anybody willing to step up, and if not, we'll go to Larry. So I don't see any hands. Oh, I see one.
There's a question for probably Danielle, but maybe the others can answer as well. There was this discussion that increase in the temperatures is going to possibly have a negative photosynthetic activity on the plant later on. Can we not mitigate that to some extent by just planting earlier? Because that's going to be another side effect, is that we're going to have a longer growing season. So could we not just shift that by planting our crops earlier and taking advantage of the cooler days earlier on in the season?
Yeah, so I think there's a lot of different mitigation strategies that we could be using to avoid that type of heat stress. So I think the one thing to consider is that, of course, the plant will still need a certain amount of time to develop and grow and produce the components that we want, right? And so you can plant earlier, and that will hopefully avoid heat stress too late in the season, but you're still at risk of increased heat events. So of course, we're seeing a lot more heat waves, as you guys are all very familiar with, things like the heat dome that we had the previous year. But also, although we're having a slightly longer growing season, the risk of frost doesn't necessarily decrease to the same extent that the increase of heat events, the risk of heat events does. And so if you plant earlier, you can absolutely take advantage of those cooler temperatures, because you'll have a warmer spring, so you can take advantage of that nice growing season. But you may still be at risk of frost damage in that very early period. So there's a little bit of it's a bit of a game, right, in how you do that, and how much risk you're going to take on from either frost stress or from planting, you know, when you're used to planting and experiencing that heat stress.
Thanks, Danielle. There's another hand up at the back of the room.
Hi, I have a question for Wolfgang. I think we are all looking for solutions to address climate change. My question is, when we design the routing systems, we have to consider the source sink balance, source sink ratio, the above ground, below ground balance. So when we thinking about put more carbon below the ground, and how that will affect the crop productivity from the energy or biomass balance point of view. Thank you.
Yeah, that's an excellent question. That is definitely on our mind when we are thinking about changing the traits and testing some of these varieties in the field. We're working on multiple species that includes canola, and each of these species is different in what we expect. And also the growing regions are different in terms of what we expect of the best balance of root mass to shoot mass to be. Like two considerations that we typically have in mind. One is, we know from screening through large collections of plant varieties that there's usually a huge diversity of root mass and shoot mass and root depth present in varieties, and so the root rates are not necessarily correlated in one way or the other with the shoot traits. And so there is I think one can assume there are genetic ways to increase both the root and the shoot mass, or to increase the root mass without decreasing the shoot mass. Now, this becomes much more interesting when we think of the field, when we think about the changing climate, because something that we know is that in many regions where we deal with terminal drought in rain-fed environments, deeper root systems will actually help to retain productivity even under drought conditions. And so those are the factors that we are actually having in mind. So it will be different in different plant species, the optimal point of root to shoot and yield then, and it will be different in different growing areas. And so by gearing up to do field trials in different parts of growing areas for these crops, we will be able to get the data that will tell us more about potential trade-offs or potential synergies in terms of deeper, more massive root systems. So yeah, I hope that was specific enough. Really, it's all about the data to acquire, and about the cropping system and the climate that you actually encounter in the growing season.
Thank you. And I just want to maybe open it up to the other speakers if they want to comment on anything that's been said so far. I guess maybe I have a question then for a couple of the speakers then. Like when we're thinking about the value of the carbon above ground versus below ground, can you kind of summarize, I guess, the relative value? Like I think it's fair to say that it's maybe more valuable below the ground, but how valuable is the above ground stover left over relative to the root system, as we're thinking about it as some of us as plant breeders?
Yeah, I can tackle that one. Like in that model that I showed, and basically from a lot of research, I guess you'd say that it doesn't seem that the assumption always is the above ground is not converted as efficiently to soil carbon as the below ground. And although there's certainly, to some extent, that may be true, but it doesn't seem to be a very large factor. It seems that the above ground does provide really valuable carbon input as well, because a lot of it is brought into the soil as it degrades physically and chemically into the soil. So yeah, that I wouldn't, I think it needs to look at the whole plant. There's obviously some advantages in increasing the roots, but I think you really need to look at the whole plant. And this is where, unfortunately, as I said, the low harvest index of canola in that sense is kind of an advantage because it does increase the above ground residue.
Thanks, Brian. So I think we'll go to some online questions, but just before that, if you are in the crowd and you do have a question, Taryn is running around with the microphone, so feel free to flag her down so you're ready to go in a couple minutes.
Okay. Very good. A lot of online questions there, 18. Really good. Some of them, they were, because everyone could vote on them, so we got 2 8s. So we try to do those 2 8s first of all. So regarding absolute emissions versus emission intensity, where does Western Canada rank on a global scale? If our emission intensity is more favorable than other regions, should we be cautious not to limit production relative to places of higher emissions? Anyone want to take that?
Okay, I can try. Like the emission intensity is per unit of production, so usually your easiest way to decrease your emission intensity is to increase your production per area anyways, or per input. So I guess I don't quite understand why reducing production would be any particular advantage other than maybe just from a supply and demand point of view of just limiting the amount of low intensity Canadian canola, and then would maybe extract a bit, but I think you just want to maximize production.
Okay, I think they're just asking, should we be cautious, not to limit production relative to places of higher emission? Okay, so second one is rates of carbon sequestration and canola residue are associated with new hybrid varieties. Is this increase influenced by higher nitrogen fertilizer use? Does higher nitrogen fertilizer use offset carbon sequestration?
I can again try to tackle that one. Yeah, it does. I mean, the increase in yield that we've seen, and it's part of the advantage of canola, as I said, sort of doubled, at least in the prairie setting over the last 4 decades. A lot of that is due to the agronomics, and a lot of that agronomics is due to better end management. So yes, you do need to have, good end fertility to provide high levels of residue production. But, as long as you can increase the grain as much or more, you still reduce that intensity. So it's, as I said, usually you're really just looking for efficient, when you're trying to reduce intensity, you're really looking for efficient production. You're not looking to necessarily change the way you're doing your inputs as much as just trying to maximize their efficiency. Usually is the quickest way. And there are techniques, and Claudia went into that, of how you can also reduce some of the emissions per unit of input. But in general, that residue versus nitrogen thing, I think it's just about increasing production.
Okay.
Yeah, if I can jump in, I think what it means for the future is that there will be a more of a focus on nitrogen, as I mentioned in my talk, because that nitrogen is needed to increase production. We're already seeing a lot of supply chain disruptions, and nitrogen is also something that the reactive forms are accumulating in the environment. So I think there will be a shift over time to focus more on doing it better with, I don't know if necessarily less, but, like having to, I think we are very focused right now is like more nitrogen is better. A colleague of mine talks like we need to shift to say that better is not necessarily more, doing it better as opposed to just more. In fact, if I can just go on a rant on this bit, if we look at that pipe and valve model, I think it's really a little crazy that we look and say, well, 50% of what is added is typically like wasted, right? Like, I know that there have been a lot of improvements, but can we not look at the industry, and particularly fertilizer industry, to come up with better products to feed into the plant, as opposed to, leave that material there in the environment to be lost? So anyway, I think that there will be in the future, there'll be a big focus on nitrogen.
Thank you. And maybe one more, Sally, when you do this one got elevated while we were talking. What incentive do we need to get canola growers to follow practices that reduce greenhouse gas emissions, CO2 and N2O, and increase carbon sequestration?
Brian, you want to go first?
I was waiting for you, Claudia. Like this.